you have sensitive electronic devices that need protection, for example, custom circuits, sensors, or chargers. If you connect them directly to the AC 220-volt power line without proper safety, a short circuit or even a fire could happen, and the result might be serious. Many people think that using a circuit breaker is enough, but a circuit breaker only cuts off power when the current exceeds a fixed threshold. That is not suitable for your DIY or customized circuits. In this video, I will guide you step by step on how to measure alternating current using an Arduino and set a protection limit that automatically cuts off the power when the current goes beyond your chosen level, helping you protect your devices and prevent possible fire risks. If you enjoy DIY projects, electronics, and want to support the channel to make more videos, please press the subscribe button and turn on the notification bell. Now, let's get started! To measure current, I will use the principle of electromagnetic induction. When the current in a conductor changes, it creates a changing magnetic field, and that magnetic field induces a voltage in my sensor coil. I tried winding a piece of wire around the conductor and measuring the signal on the oscilloscope, but nothing changed. The reason is that in an AC power wire, there are two conductors, a live wire and a neutral wire, with currents flowing in opposite directions. These opposite currents generate opposing magnetic fields, which cancel each other out. As a result, the sensor coil does not pick up any signal at all. I tried winding the coil around a single wire to avoid the cancellation effect, but when I measured it on the oscilloscope, the result was the same, no signal at all. I thought it might be because the number of turns was too low, so I switched to enameled copper wire and wound more turns. But it still made no difference. So where did I go wrong? After trying many ways and still not seeing a signal, I began to suspect my winding method. In fact, when I wind the coil straight around the conductor, the magnetic field of the current circles around the wire, rather than passing through the coil. According to Faraday's law of electromagnetic induction, a voltage is only induced when a changing magnetic flux passes through the coil. In this case, since the magnetic flux does not pass through the coil, the result is that no induced voltage is generated. To solve this, I used a hollow toroidal ferrite core similar to the core in a toroidal transformer. I wound many turns of copper wire around the core and passed a single conductor through the center of the core. Now, the current in the wire generates magnetic flux that runs through the core, and my coil clearly senses a voltage just as Faraday described. In fact, the alternating current sensors available on the market also work based on the principle of electromagnetic induction. For convenience, I bought a ZMCT103C sensor. Inside it is a mini current transformer core, wound very evenly with an accurate turns ratio. Thanks to that, I can easily calculate the actual current simply by measuring the output voltage of the sensor and multiplying it by the known conversion factor. You can see that the signal obtained from the ZMCT103C sensor is a series of sharp pulses at 50 Hz. This happens because the induced voltage only appears when the current in the circuit changes direction, producing sharp peaks instead of a smooth sine wave. A signal like this is very difficult to measure or calculate accurately because the values change too quickly. To fix this, I will add a burden resistor across the two ends of the sensor coil. This resistor converts the induced current into a voltage proportional to the actual current, and also smooths the signal to make it easier to measure. After adding the resistor, the signal becomes a more regular sine wave, which is ideal for the Arduino to read and process. Next, I will use the ADC on the Arduino to measure the waveform obtained from the sensor. But there is a small problem. The current waveform is alternating current, while the Arduino ADC can only read positive voltages from 0 to 5 volts. This means that if I feed the AC signal directly, the negative part of the voltage will be cut off, and it could even damage the Arduino. To solve this, I will use a voltage level shifting circuit called a clamper, using an op-amp, as shown in the diagram here. This circuit shifts the entire AC waveform upwards, so the signal fits entirely within the 0 to 5 volt range, safe for the Arduino to read with the ADC. So how does this clamper circuit work? Let's analyze it in detail right now. Suppose I have an alternating current signal with an amplitude from -2 volts to +2 volts at the input. Now, if I want to shift this entire signal upwards, I can do a simple experiment. I use a 1.5 volt battery, connecting the negative end of the battery to the input signal, and the positive end becomes the output. When measured, you will see that the entire signal is shifted up exactly by the voltage of the battery, so now it oscillates from -0.5 volts to +3.5 volts. Of course, in a real circuit we cannot use a battery like this because the voltage would not be stable and would not automatically adjust according to the signal. Instead, people use a capacitor and a diode to create a similar effect. The capacitor stores and holds a DC offset, which shifts the signal above 0 volts. To do this more stably and accurately, we use a clamper circuit with an op-amp that works on the same principle. Here is the op-amp clamper circuit diagram, which I will analyze in detail next. Initially, the input signal rises from 0 to +2 volts. At this moment, the capacitor is not yet charged, so it allows current to pass through. Because the input impedance of the op-amp is very high, almost the entire input signal appears at the output. In other words, the output voltage is nearly identical to the input voltage. At this point, the voltage at the inverting input of the op-amp is higher than at the non-inverting input, so the op-amp output is pulled down to a low level, close to 0 volts. Since there is a diode blocking the reverse direction, the output signal cannot flow back into the op-amp. Therefore, during the positive half cycle, the output signal almost matches the input signal. Now, when the input signal drops below 0 volts, the voltage at the inverting input becomes lower than at the non-inverting input, causing the op-amp to reverse its action. The output rises to a positive voltage. This positive voltage passes through the diode to charge the capacitor, keeping the right side of the capacitor as close to ground as possible. This charges the capacitor with a voltage equal to the lowest negative amplitude of the input signal. When the signal reaches its minimum value of -2 volts, the left side of the capacitor has a voltage of -2 volts, while the right side is held near 0 volts. At this point, the capacitor is charged to about 2 volts. It can be considered a 2-volt battery connected in series with the signal. From then on, the entire input signal is shifted up by a 2-volt DC offset, meaning it is completely lifted above 0 volts. And if during operation the voltage drops or drifts slightly, the op-amp automatically adjusts, increasing the output and charging the capacitor further to maintain a stable offset. A very smart and effective feedback mechanism. The current output signal is quite weak. If I feed it directly into the Arduino ADC, the ADC circuit itself will cause the signal to degrade significantly. To solve this, I added a buffer circuit using an op-amp. And since the LM358 already has 2 integrated op-amps, I can conveniently use one of them. Now, let's solder the clamper circuit in practice and see the results. Oh, the output signal is stuck at a high level, and there is no visible oscillation at all. This is a mistake that I think many of you will encounter when trying this circuit. The reason is that the inverting input of the op-amp is left floating, without a resistor pulling it down to ground. In this case, the op-amp does not have a clear reference voltage, causing the output to saturate and stick at a high level. The fix is very simple, just add a resistor of a few hundred kiloohms from the inverting input to ground. Now the op-amp has a stable reference point, and the circuit works exactly as expected. Here is the overall circuit diagram that I have designed. It may look a bit messy at first, but actually it is divided into very clear sections. The ZMCT103C sensor measures AC current. The clamper and buffer circuits using op-amps shift the signal level and strengthen it before feeding it into the Arduino. The Arduino processes the signal and performs calculations. The OLED screen displays the values. The rotary encoder is used to set the automatic current cutoff threshold. The relay switches the load power on or off when the threshold is exceeded. The buzzer sounds an alarm when the load goes over the set limit. The high-link power supply converts AC 220 volts to 5 volts to provide stable power for the Arduino and modules. Now, let's start soldering the circuit. Next, I will program the Arduino. Since this video is already quite long, I will not explain the code in detail here. If you want me to go deeper into the programming part, please leave a comment below. I will make a separate part 2 just for that. And now, let's upload the code and test the real circuit to see how it works. The display interface includes the following sections. The top line shows the real-time current and power being measured. The second line shows the protection threshold. If the load exceeds this limit, the relay will automatically turn off to protect the equipment. This threshold can be set either by current or by power. The bottom line shows the operating status. OK means the system is running normally, and trip means an overcurrent has occurred. To set the threshold, press and hold the button for about 2 seconds, then rotate the knob to change the value. Hold it again to switch to adjusting the threshold by power in watts, and hold it once more to return to the normal measurement mode. While adjusting, you can short press the button to switch the step size between increase and decrease units. After the adjustment, the threshold value is saved into the Arduino's EEPROM memory, so even if the power is disconnected, the setting will still be preserved. All right, now let's test it with an induction cooker. As you can see, the measured values are very accurate, right? I set the limit to 1600 watts. And when I increased the power to the maximum, the cooker consumed about 1696 watts, exceeding the limit. Immediately, the relay switched off. That means the circuit is working very stably and precisely. Now, let's try it with a few other loads and see how it performs. So, we've just completed an AC overcurrent protection circuit, capable of measuring current, power, and automatically cutting off the load when it exceeds your preset limit. With this circuit, you can protect your DIY electronic devices, or use it as a foundation for more advanced projects, such as a smart protection socket, an automatic breaker panel, or even a whole house power monitoring system. If you find this project useful, please give it a like to support me, and subscribe to the channel so you won't miss part 2, where I'll explain the Arduino code in detail, and share a few signal processing tricks to make the measurement even more accurate. Thanks for watching all the way to the end, and see you again in the next project.